Okay, so next we're going to talk about loops, and Santosh Pande will tell you about beacons.
Thank you so much. It's great to be here, and good evening. My name is Santosh Pande from Georgia Tech, and I'm the last author of this, but all the other previous authors couldn't make it, and because of visa reasons, but I do want to acknowledge Chris, who finally made it here. So I want to introduce the motivation, and this is a different kind of compiler work. Unlike traditionally optimizing a single source program, its influence is in terms of improving the schedulability of HPC workloads on shared high-performance machines, which is a very difficult problem, which has been outstanding since I started my PhD almost, I don't want to tell you how long. But at the root of the problem, I'll tell you what lies, and that's the PL problem at heart, which we have solved first time in this work, which is about the loops and their dynamic characteristics. So here are the main contributions of this particular work. It's a compiler-directed predictive analysis, which estimates the dynamic resource requirements, but just in time for every instance of execution before that execution happens. At the heart of the analysis is loop trip count prediction dynamically. How many a particular loop will execute, how many times it will execute. And I'll tell you why it is a very difficult problem and how many loops fall in this category. And that has been done with a combination of static analysis combined with machine learning and dynamic specialization just in time for that loop. And then finally, it's applied in a scheduling discipline. How do you co-schedule certain independent processes together at runtime to maximize the utilization of the system, as well as reducing the speeding of the throughput of the whole batch of processes which are getting scheduled so that the user queues, which are heard currently on an HPC system, are speeded up. So what happens really on the current set of HPC systems, those who may be not familiar, is everybody secures their own cluster by going through Slurm, which is the scheduling system used across all national labs and all supercomputing centers, gets a part of that particular cube for their execution. And how do you decide the size of that and so on is left to, of course, the scientific programmer. They use profiling, they use their own domain knowledge, and so on. And obviously, as per their peak demand of resources, as per their estimation, they get it. So most of the time, it's idling outside of some of these regions. And not only that, no phase co-execution is taken into an account. For example, if you and me are sharing a system, it could be very well be that my peak demand occurs at a different time than yours during the execution, so why not share the system? So these are the reasons why dedicated things are underutilized, and it leads to a huge underutilization. We spend millions and millions of dollars in terms of building these systems, but they go heavily underutilized. And not only that, after spending all this money, scientists have to wait for weeks sometime to get their job scheduled, especially if the size is large. So this is the extent of this problem, and I think just wanted to show that compiler can play a huge role here, which is a non-traditional role. So this is why we introduced this beacons framework, which is a cooperative framework. A lot of it is static analysis, and then at execution time or runtime, it instrumented beacons, broadcast their characteristics of the forthcoming loops, and that get combined and leads to a workload scheduling system, which really improves the throughput almost by 2x. So here is what happens in terms of overview of static analysis. So this is what we call as a predictive analysis, which instruments these beacons at the entrances of the loop nests. And the idea here is to be able to first predict the loop trip count of the forthcoming loop nest. Why that is a hard problem? We'll come to that. We use static analysis, SSA-based static analysis as LVM IR level, combine it with ML and generate some of these models which sit there and predict the trip counts. Then we use these predicted trip counts and generate a loop timing model, which is very interesting to determine how long this particular loop will take, an estimation thereof, a loop nest. We generate that. We generate the memory footprint analysis. We leverage polyhedral model and enhance it by using predicted loop counts, trip counts to find out the memory footprints, which is not possible for many loops currently, given their unanalyzability because of trip count non-determination. Then we use reuse distance, which is again used for deciding the data reuse behavior in the caches. So all this happens through static analysis. We instrument these loops through different models or closed forms, and the lightest prediction mechanism that we can think of at the entrances of the loop. From there, the beacons library is synthesized by the compiler, which sits at the top of each loop nest. So this is the static part. Now at dynamic or runtime, every time the loop nest is encountered at execution time, every instance of it, it could behave differently. And the studies have shown that, in fact, the variance could be very big because underlying is a numerical method. Sometimes it terminates during thousands of iterations. Sometimes it could take millions of iterations and so on for the exact same loop nest. So we predict this, how many iterations it will take, and that's basically the interesting part of this loop trip count prediction work. So once we predict that, we predict all the other characteristics of the loop. The beacons library then sends all this to the scheduler. The scheduler finds out what is going on in the multi-core system in terms of resource allocation done to different processes, where they are, what kind of footprints they have, what kind of timings they have, and then based on that, it decides the scheduling decisions, and we'll come to that part. So this is built into LLVM, so this is the compiler flow of it, which I will skip because this is pretty much given, the detailed algorithms are given in the papers, and I will illustrate some of this through some examples, which will make at least the important highlights very clear. I will defer the details of the algorithms, correctness, etc. In the paper. So let's start with something very interesting. And here are different kinds of loops that we encounter in scientific codes. What I want to draw your attention to is, if I can focus on this. So leftmost loop, or NB loop, which is on this side, where I had pointed my cursor earlier. So that one is a fixed trip count loop, symbolically unknown, but we know that it will symbolically execute for U minus L kind of iterations, and the compiler can generate this type of formula very easily. This is the regular loop, which was there, which has been tackled a lot by HPC compiler optimizations people, but just except out of these, everything else is untackled. Why? Okay, let's go to the next one. This is a while loop, which has a loop body, and it iterates and iterates, and unless this particular condition is satisfied, it doesn't terminate. So the trip count cannot be statically estimated, period. So nothing can be done about it. How about dynamically? No, not currently. And that's what this paper does, is in terms of not exact determination, but an estimation, how much of this while loop will execute. And how is that possible? Well, what we have done here is, and I'll come to that part in a minute, is identified the critical variables on which the iterations depend, which is these two array elements, and then did static analysis to project them into the state which is existent here right before the loop, and using that and machine learning, generated a model that, given those dynamic values, what happens to these loop trip count. Now, the next loop is a regular in terms of 0 to parameters type of a loop, straightforward, just like the first one, but it terminates in an irregular way. Why? Because it has this particular condition, which is an exit condition out of the loop. So how many iterations it executes at runtime? Worst case is this minus this number of parameters, but in actuality, it will terminate prematurely. Now, if you take worst case into an account, you get into, again, the scheduling decisions, which are very conservative. If you predict it, and if you predict it well, you can aggressively do the scheduling using this particular thing. Now, traditional compiler optimizations or analysis, why did it ignore some of this and just took a worst case view of this type of situation or this? Because they are relying on program transformations and they need a guarantee. Of course, the methods that we developed do not have guarantees. No ML can give you any guarantee. But they give you a pretty accurate behavior estimate in using which you can do scheduling. So what happens if you go wrong? Well, it's not a soundness issue. It's simply a performance issue. You are executing under some conditions which you didn't anticipate. And there are recovery mechanisms of descheduling and other things, but it doesn't affect the result. And if you are accurate, which is what we'll show, you gain a lot in terms of resource utilization. So the last loop is even worse. It's basically a combination of going in a linked list using pointers, and then there are termination conditions. The workloads, is if you really understand these different types of loops, in very primitive times, they were in the fixed trip count region, just like this. But all the modern workloads are going more and more and in this particular category. And so this problem needs to be really tackled in terms of categorizing these loops and trying to predict their behaviors. Okay, how does this happen inside a compiler setting, having motivated that such loops are really predominant? And by the way, one part which I missed was they are about 55% of all the workloads in the benchmarks that we studied, and some of the other benchmarks, like the modern ones using ML and all, they are even higher percentage-wise. So how do we really deal with this? Here is a simple code, which is, again, do-while type of things, which doesn't give us the trip counts even dynamically. But what you can see here is this, that the branch conditions and the exit conditions, which are E equal to F, if you backward slice it using SSA, and I deliberately just kept it in a non-SSA form here, just to make the point, it projects onto A and B, and the other condition projects onto C and D in a backward sense by doing the analysis and by finding out the variables which are live here, which determine this branch. So if you take this A, B, C, D over here and do some training and correlate it to the termination condition and generate a model, that should be able to predict this. And that's what pretty much the approach does. So here is more concrete examination of this problem, the ML part of it. So what we do is we do this training by generating these feature sets, which are these variables, which are backward slice. The compiler produces these. They are used for training, and we generate simple model, which is a classification type of a model, which has very lightweight things, and it maps it to the loop trip counts, which is the label here. And the great part of it, and this is discussed in the paper, is unlike loop profiling or any regression-based approaches, this extrapolates the distribution of what you see in terms of the values here versus the trip counts in a very nice way. By the way, this example and other example in a benchmark also show that the trip counts fluctuate dramatically during the execution. But it also shows that the number of such trip counts, unique trip counts, is not a huge unbounded number. It actually tends to be a fixed number. So all these internal values, whatever you see here, they fall into just a few of these bins over here in terms of trip counts. So that solves one part of finding the trip count, and the algorithms, the classification, the techniques which backslice them, find out the feature vectors, and then use them for training, for ML. They're all discussed in the paper. But it doesn't solve there. It doesn't stop there in terms of the problem to be solved. The important problem to be solved really is, for scheduling purpose at least, is loop timing. That can you really determine the loop timing of a nested loop? And the answer to that is, because there are 55% loops, once you get, which are irregular, once you get the trip counts, you can generate a timing equation for this particular loop, and in fact learn on it too. So why is that the case? Well, the loopness or the trip counts are correlated or anti-correlated in many cases. For example, if the inner induction variable is j, which is derived out of outer variable I, then the inner loop's execution, as we know in trapezoidal loops or triangular loops, is affected by the outer loop. And such things become more complicated because of the data flow and conditions which control the data flow. And if that can be learned by using these predicted trip counts and put it into an equation, that allows you to find out the overall timing of this particular loop nest. So at runtime, using these particular values, the loop bounds are then plugged in to generate the timing. And now we are ready to do one last thing, which is the footprint, which is important for a loop. And the second thing, what kind of loop it is we must classify. So the footprint is not possible to capture unless the trip count is. But if you have the polymorphic model, which is a lot of affine references inside the loop and the trip count, you are able to find out the overall footprint of the cache usage of this loop. Now, does that end the matter there in terms of shared cache allocation? It doesn't, because it depends what is going on inside the cache. And again, by using the trip counts, which sometimes serves as the reuse distance of a particular inner loop, one is able to find out what kind of reuse distance is that. If it's a small one, we don't care, because it's a streaming loop. If it's a large one, if there's a very large loop sitting in between two references which may have reuse, we will have an issue in terms of losing that cache locality. And so we classify the inner loops into reuse loops and streaming loops by using this. And then we have the second component of this, which is a scheduler, which has two modes, a reuse mode and a streaming mode. So what happens is, if the reuse distance is small, we classify it as a streaming, and then we maximize the concurrency here in the reuse mode. However, we do not allow the cache to become stressed so that it causes thrashing. Now again, why is it possible to use the compiler knowledge in deciding this? First of all, the classification is dependent on the knowledge of the trip counts. Second is, the footprint is directly proportional to this, the trip count. And the third thing is, the loop timings are dependent on it. So let me go to quick results. So how accurate is this prediction? That's the first question in terms of this. You can see that the prediction is very high in terms of 80% accuracy, and allows you to do a great prediction by using this particular technique in terms of the trip counts, and this facilitates best scheduling. So I'm going to focus on the loop timing prediction, which is also equally accurate. As you can see, especially for ML, it's over 95% accuracy in many cases. And the third one is the end result, which I wanted to show. So we have compared this against state-of-the-art reactive scheduler, which reacts to the performance loss at runtime, which is the current research practice, and even commercial practice, which is CFS, which comes with the Linux distribution that is deployed in all the research center, the national labs and all the supercomputing facilities. And you can see that we outperform, this is our scheduler, by a factor of almost 2x on an average with the commercial one, and almost 3x on the other one, the research one. So finally, to conclude, the loop trip count prediction matters. And because it's 55 or 60%, sometimes loops are indeterminable or unanalyzable by compiler. What we can do here is, in the prediction side, use static analysis combined with the ML to do this. That helps to solve all the other related problems, and that in turn facilitates this type of a scheduler, which is a significant improvement in terms of the throughput improvement is exactly the same as the utilization improvement, because you can see that the amount of time spent on that machine by that batch is cut in half, so, and the resources are used better. Just as a last remark, we have been working in this area for solving different problems. Everywhere there is a GPU shortage and unavailability, even on supercomputing centers. And so the question is, how can we safely share? We had a paper in PPOP, and of course, the other one which we had was PACT, which was sharing the cache. Thank you so much.